Good day, Intro to Mathematical Statistics students. This video covers Chapter 9 in your textbooks, 1 and 2 Sample Estimation Problems. So today we're diving into a very important part of statistics, and that is estimation, how we use our sample information in order to make educated statements about the entire population. So in this chapter, we're going to focus on confidence intervals specifically, prediction intervals, comparing two population means. And all of these tools, when you put them together, it's going to allow us to estimate our unknown parameters with a known level of uncertainty, okay? So by the end of this lesson, you're not going to only understand how to compute each interval, but also when and also why we would need to use each type. Okay, let's jump right in. First, our definition of statistical inference. It consists of those methods by which one makes inferences or generalizations about a population. Okay, so everything we cover is going to revolve around how we estimate our unknown population using our sample data. So this leads directly into statistical inferences, okay? So it may be divided into two major areas, estimation and also hypothesis testing. If you've done Stats 2, then you certainly know all about that. Okay, so we break it down into two main categories. So we're not going to be doing hypothesis testing today. We're going to focus on the estimation side. Okay, so a key in estimation is, of course, the concept of a point estimate. You learned this in Stats 2 as well. The point estimate of some population is that single parameter, and we have a new way of writing it this term. I know in statistics you're used to seeing a different variable here. Now you have theta with a little cap on top of it. Okay, so when you see that, you know that that is the denotation for a point estimate, right? So here's our interval. It has a lower bound, which we have our point estimate with an L there indicating lower bound. And then we have our upper bound, which has a U in that space. It's computed from a selected sample. Of course, we're given an interval. And this is important. Let's not just bypass this part here. Whatever your confidence interval is, your alpha value is going to be the difference between the confidence interval and 1. Okay, we're going to definitely need that. And so we get our upper and lower confidence limits, or they are denoted in this way. Okay, so here's our areas of concentration. Notice how we're going to be using negative z sub alpha, rather, and we're also going to be using positive z sub alpha. Okay, so now we know what our mean is, right? But we never talked about the reliability of the data. So along with the mean, we often have an interval of numbers. So I may say, I know that my sample mean isn't going to be equal to the population mean exactly, but there's a 95% chance it would be in this interval. Whatever that mean is, there's a 85% chance it would be on this line somewhere, a 99% chance. So now, along with our estimate of what our mean could be, we're also going to have an interval along with a percentage of certainty that our population mean lies in that interval. Okay? All right, let's look at example 1. The average zinc concentration recovered from a sample of measurements taken in 36 different locations in a river is found to be 2.6 grams per millimeter. Find a 95% and a 99% confidence interval for the mean zinc concentration in the river. Assume that the population standard deviation is 0.3 grams per millimeter. Okay, so there's a lot of different things that we have here. Let's point out what we have first, what is obvious. We have 36 as our sample size. So let's go ahead and identify our N to be 36. Okay, we have, what else here? 2.6, okay? The average zinc concentration recovered from this sample is 2.6. So we have our sample mean, 2.6. I'm going to jump down here and identify the population standard deviation, 0.3. And now we do have to get our z sub alpha value. Let's tackle 95% first, okay? The first thing that we need is our alpha value. So alpha, we already stated, is 1 minus the confidence level. So our first confidence level is 95%. So alpha is 1 minus that 95%, or 0.05, okay? So now, pay attention. We have a formula, and we're going to use that formula exactly, okay? In this formula, you see we need an X bar. We found that. We need a sample size. We have that. We have a population standard deviation. We have that. So the only thing that we need to find before plugging into this is z sub alpha divided by 2, okay? So we have our alpha. So z sub alpha divided by 2 would be z sub alpha, which is 0.05, divided in half. That is z sub 0.025. All right, now some charts already have this number, okay? Some of you may already know that that corresponds to 1.96, okay? If you remember in statistics, there's a common tabled area here. See that? Z sub 0, without the owner, cancel. Okay. Z sub 0.025, 1.96. You could just remember that every time you do this and you get 95% concentration, it's going to be 1.96 if you're finding the Z value. Or you could find it manually, and let me show you how to do that, okay? So if you had to find this manually, you didn't already know that it was 1.96, how would you compute z sub alpha notation? Okay, well, you know that this value is the area to the right, and the chart gives us areas to the left. So first you must subtract that value from 1. That gives us 0.975. And then I go looking in my chart. Okay, this only goes up to 50%, so let's go to the next one. 0.975, 0.975. Okay, so it looks like it's right there. 0.975. 1.9, goodness gracious, 6. Without the owner password, you do not have permission to save this. Okay, do you see, I'm not going to be able to write on this. I'm not sure why, but do you see 1.96? Hopefully you see that. 1.96. Okay, that's going to be annoying me the whole time. Anyway, so that's how you would get it if you had to do it the long way, okay? All right, but anyway, now we have everything we need. So what is that formula? X bar plus and minus z sub alpha divided by 2 multiplied by sigma divided by square root n. So let's put everything in. Our x bar, 2.6. Our z sub alpha divided by 2 value, 1.96. R sigma, 0.3. Rn, 36. All right, let's plug this in and get our interval. It's just as simple as that. So that would be 2.6. I'll do minus first. Minus 1.96 multiplied by 0.3 over the square root of 36. Okay, so our lower endpoint is 2.502. And let's do that same thing with the plus 2.698. Lower endpoint, 2.502. And our upper endpoint is 2.698. All right, so I believe that's it. Let's just check and see. Yep, 2.698. And I believe that first was 2.502. Okay, fine. Okay, the other thing that they asked us to do was find a 99% confidence interval. Okay, so we're doing the exact same thing. The only difference is we're using 99%. Okay, so the only difference is now we need a new alpha value. The other things are not going to change. It's basically just the z sub alpha value that will change. So at 99% confidence, we've got 1 minus 99%, which is 0.01. And that z sub 0.01 divided in half gives me z sub 0.005. Okay, so if you're not sure that's 2.576, I believe, then we can do it the long way, which is to subtract our alpha value from 1. That takes us to the chart. One minus 0.005. Okay, 0.995. Let's go look and see. 0.995. Okay, so pay attention here. We have 0.9949 and 0.9951. Okay, it's directly in between those two, so it is 2.575. Okay, I hope that that's clear because I'm not able to write on here, but this one is completely equidistant. I want to know how to unlock this document. I don't know if I'm going to be able to. Let me see if I have it someplace else, because that's going to drive me crazy. There, good, my goodness. Okay, now we're in business. Okay, so here's where we were. We were trying to find 0.995. If you look here, normally we go with the closest, but 0.9949 and 0.9951 are the same distance away from 0.9950. So this first one, 0.9949, is associated with 2.57. The second one is associated with 2.58. So when this happens, you have to get the average of the two. So it would be 2.57 plus 2.58 divided in half. Okay? Hopefully you know that's just 2.57 and a half. Okay? So 2.575. All right, the rest of it is the exact same. I'm literally plugging in here exactly as we did before. I still have my mean value, which is 2.6. I still have the standard deviation population and all of that, still have all that. The only difference is my z sub alpha value is now 2.575. Okay. All right. Let's go back to our calculator. 2.6. Let's do minus first. Minus 2.575. And that is multiplied by 0.3 over square root 36. So my lower bound this time is approximately 2.471. And the upper bound is 2.729. And we're done. Okay, so the confidence interval. So we expect that our sampling error, that our sample mean would have error, but we can be 95% sure that whatever the population mean is, it lies between these values. And we can be 99% certain that whatever the population mean is, it lies between these values. Okay, that is the confidence interval we just had. So yes, we expect that our sample will have some error, but along with that sampling, along with our sample mean, now we have an interval that we could put a confidence level on. So I can say with 95% certainty that my population mean will lie in here, okay? With 99% certainty, I believe my population will lie in there, okay? All right, often in statistics, the statistician will be concerned with how many people should I ask? I'm doing a sample and I want to make sure that my sample is within a certain error limit. I have a certain standard deviation. I have a certain z sub alpha score. How many people should I ask? Well, there is a formula now that makes it quite easy to determine how many people you should ask based on a given set of parameters. Now, one thing that's important here is that when you plug into this formula, you have to round up to the nearest whole number. This n, as you remember, represents a sample size. So if you're trying to find out how many people to ask, certainly you can't ask 3.5 people, right? So for this formula, every single time you use it, you must round up to the nearest whole number, okay? All right, how large of a sample is required if I want to be 95% confident that our estimate in example 1 is off by less than 0.5. All right, so what are the things that we have here? Well, first, we do have a confidence level, 95, okay? We have our estimate our error estimate, so our E value, that's 0.05. And they want us to use the data in example 1 again. So if you remember, in example 1, our population standard deviation was 0.3. All right, we have a nice tidy formula right here. And I hope you understand we've got 95% confidence again. So we've already found the Z sub alpha for that. We know it's 1.96. Okay, if you need to, pause the video and refer back to us just finding that, getting the alpha, going to the chart, determining that it was 1.96. We have that already. So we have 1.96, so we have this part of it. We have our sample, population standard deviation, and we have an error value of 0.5. So really, all I need to do is just plug into that formula, okay? I'll do it right here while you're looking at the formula to make it easy for you to compute what's going on, okay? So we've got sigma 0.3. Our error is, we said, within 0.5. Notice I got that right here. And we want to be 95% confident. So alpha is 0.05 and Z sub alpha divided by 2, we've already done this, is 1.96. All right, let's plug everything in. So our N is equal to 1.96 multiplied by 0.3 divided by 0.05, and we're squaring that. Let's see what we get. .96 times 0.3 over 0.005, over 0.05, close bracket squared. So 138.2976, but we already said for solving for n in this situation, we always round up to the nearest whole. Even if that was 138.002, any part of the next number and we round up. Okay, it's not the traditional rounding where if it's above 5, you round up, and if it's below 5, you say the same. No, when you are doing solving for n, solving for the sample size, you always round up. Answer, 139 people. And we're done. All right, let's keep going. So the confidence intervals and resulting confidence bounds discussed so far are two-sided. Notice how we had an upper endpoint and a lower endpoint of our confidence interval. But sometimes you may just have an upper bound or just have a lower bound. In that case, here is the formula. Now notice the key difference. In all of the examples that we did before this one, our alpha, our Z sub alpha value was divided by 2. Now it's just Z sub alpha. It is not divided by 2. So if I have just an upper bound or just a lower bound, the main difference is I do not need to divide my alpha value in half. All right, let's do it. Notice how for this one, I only am asking for an upper bound at 95%. Okay, so let's look at all of the things that we have. First of all, we've got 25 subjects. So our sample size is 25. What else do we have? In a psychological testing experiment, 25 subjects are selected randomly, and their reaction time to a particular stimulus, they didn't say what it was, but it's measured. Past experience suggests that the variance, pay attention, the variance is 4 seconds squared. So listen. They gave us the variance, but there is no space for variance in this formula. We don't have variance. We have standard deviation. So hopefully you remember from the last section the relationship between variance and standard deviation. Okay, the variance, theta squared, is 4. So my standard deviation is the square root of my variance, which is just 2. Okay, so we have our standard deviation, my average, so there's my mean there, 6.2. Okay, they want a 95% upper bound. Well, what do? Once we get our confidence level, we immediately find alpha. 1 minus 0.95 is 0.05. This time, we are not dividing it in half. We just need to find z sub 0.05. Okay, you may already know that's 1.6, what is it, 1.645? If you don't already know that, fine, let's go to the chart. In order to go to the chart, I need to get the left area. Okay, so that is 1 minus 0.05, which gives us 0.9500. And now to the chart. .9500, which is the closest. Do you see? It happened again. Look here. Let me erase all this so you'll see where I am. I'm looking for the closest value to 0.9500. Both of these values, no, not that one. I underlined the wrong thing. Both of these values, 0.9495 and 0.9505, both of those are equally distant away from 0.9500. Now, this is a statistics 1 concept, but just in case you've forgotten, the z-score that goes with 0.9495 is 1.64. And the z-score that goes with 0.9505 is 1.65. Since they're equally distant away, I get the average, and that's what 1.645. That's where that comes from. All right. Okay. They asked me for an upper bound, so I'm going to use my upper bound formula exactly. You see it sitting right here. This formula right there. Okay? So let's plug into that using the values that we have. X bar plus z sub alpha times sigma over square root n. So x bar is 6.2. Our z sub alpha value we just found to be 1.645. Sigma is 2. And the n value, 25. Just using all of the things we just found here. Plugging them all in. Okay, let's get our final answer. 6.2 plus 1.645 multiplied by 2 divided by the square root of 25, 6.858. And that's actually our only answer for this one, because they only asked for an upper bound. And that's it. Hopefully that makes sense. You know, this confidence interval, this upper bound gives us the highest, value in that interval. Okay. Now, all of the values or the confidence intervals that we found a second ago are for z sub alpha, when our population standard deviation is known. But what if I don't know what it is, right? If I don't know what it is, then instead of the z distribution, I would be using t instead. There are a lot of similarities, but notice Our z sub alpha divided by 2 is replaced with the t sub alpha divided by 2. Our sigma, or our population standard deviation, has been replaced with S, our sample standard deviation. Everything else is the same, but notice when we go to the t-chart, we also do need the number of degrees of freedom, which is always our sample size minus 1. Okay? So, look at this one now. The contents of 7 similar containers of sulfuric acid are 9.8, 10.2, 10.4, 9.8. You see the values there. Find a 95% confidence interval for the mean contents of all such containers, assuming it is approximately normal. All right, I don't know what calculator you have. Hopefully you are using the TI 36 so that you could very easily calculate what our mean and our standard deviation is here. We don't have those values, and so we know in order to finish it, we've got to use the calculator to find those values. I can do it offline. If you have the TI 36, though, just as a refresher, you would press your data button, and then as soon as you press your data button, you should see a list and an area for you to add in all of your values. Okay, I don't have an online calculator that can do it, so let's see if we can find one. Okay. So it doesn't matter. We could just pick any one of these. So let's enter our values, 9.8. Now you're doing this in your calculator, hopefully, so that you don't have to do it manually. 10.2, 10.4, 9.8, 10, 10.2, and 9.6. Okay. So we've got a mean of 10 and a variance of 0.08, but we need our standard deviation. Oh, perfect. They gave us that. So standard deviation, 0.283. Remember that. And then our mean is just 10. Okay? Hopefully your calculator gave you those same exact values. All right, so our mean, sample mean, is 10, and our sample standard deviation is 0.283. Okay, well, let's look at our previous formula. This is exactly what we're plugging in. We need to find T sub alpha divided by 2. We have everything else. Okay, you see our sample size. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 7 numbers. Make sure I plugged in all 7. Yes, so N is indeed 7. Good. And so now we just need T sub alpha. Okay, how do I get alpha? By dividing, or subtracting rather, our confidence interval from 1. That gives me 0.05. I am dividing that in half. So 0.05 divided in half is T sub 0.025. And what is my degree of freedom? Well, my degree of freedom is N minus 1. There are a total of 7 people, and so degree freedom 6. All right, let's go to our chart. We have T sub 0.025, degree freedom 6. Okay. Do I not have the T chart? Oh dear. Okay. I don't have the T chart with that one, so sadly, I'm going to have to go with this one. So pay attention because it's not going to let me write, okay? I need T sub 0.025 You see it right here in the center of the screen with degree freedom 7 minus 1 or 6. Can you see that that's 2.447? Okay, 2.447, degree freedom 6, and T sub 0.025. 2.447. All right. So T sub alpha divided by 2 is 2.447. All right, using this formula exactly, let's get our confidence interval. So x bar plus and minus T sub alpha divided by 2 multiplied by S divided by square root n. Our sample mean is 10. Our T sub alpha divided by 2 value is 2.447. Our S value is 0.283. Our sample size is 7. Okay, let's plug all this in and see what interval we get. 10 minus 2.447 multiplied by 0.283 divided by the square root of 7. Lower bound 9.738. Upper bound 10.263. And we're done. Okay, that's it. You know, it's pretty straightforward. Chapter 9 is all confidence intervals. I mean, that's the only thing we're going to be doing. Okay, confidence intervals. Let's go on. So suppose we have a large sample confidence interval. So our n value is greater than or equal to 30. Again, our population standard deviation is unknown. So we have this formula, okay, that can be used. And it's just important that you know there are a lot of similarities between the formulas, but there are also characteristics, right? Characteristics when you can and cannot use a specific formula, okay? So if I have an n greater than 30, so often, even when I can't assume normality, I can use the normal distribution, okay? It may be used. So let's use it now. I have a sample of 500. As we find this information out, let's just go ahead and write it down. My n is 500, okay? I've got SAT scores, 500 students. The sample mean is 501. The sample standard deviation is 112. Okay. %99 confidence interval. All right. Well, let's do it. 99% confidence interval. Alpha is 1 minus 0.99, which is 0.01. Look at the formula though, okay? The formula says z sub alpha divided by 2. So that would be z sub 0.01 divided in half, or z sub 0.005. Okay, Now, I hope that you remember, we've done this several times now in this lesson here. Whenever you see Z sub alpha notation, this is asking you to find the z-score with 0.005 to its right. Okay? The chart only gives us areas to the left. So that's why I have to figure out what the area is to the right, and figure out what the area is to the left by subtracting the area to the right from 1 and then looking to see which z-score is closest, okay? So clearly we have here 1 minus 0.005, okay? So that gives us 0.995. I feel like we've done this already. Did we have a z-score of 0.995 already? Yes. See that? We already found this. We go to the chart again, we're going to get the same exact thing. Sorry about that. So we went to the chart already and found the z-score for z sub 0.05, 2.575. We already have that. So I'm just going to go ahead and use that as opposed to going to the chart again. It's not going to change for what we're doing now. Oh, goodness, it erased everything. Okay, that's all right. I'm just going to plug directly into it, okay? We already have those values. Hopefully you've written it down on your paper, okay? So our sample mean for this was 501. Plus and minus the 2.575 value that we had that I looked from our previous example. That's multiplied by the S, or our sample standard deviation, which is 112. And that's divided by the square root of our sample size, which is 500. Okay, let's go ahead and plug that in. 501. I'll do minus first. Minus 2.575 multiplied by the S value divided by the square root of our sample size. 488.102 is our lower bound. So we know that our population mean is going to lie between that number and 513.898. And this is our confidence interval for this problem. There are a lot of similarities. You may be able to just jump to the end, I mean, if you want to, but I just want to make sure you're with me on this, okay? If you have sample data, if you have population data, if you're asked for an upper bound and a lower bound, or if you're just asked for one or the other, there are different formulas. You will receive all of the formulas, so all you have to do is remember to plug it in. You know, the sample mean, sample standard deviation, population mean, standard deviation, all that is going to be very simple to find. So really, or it's going to be given rather, the only thing you have to look up is what the z-score is, or what the t value is based on the confidence level that you've been given. That's the only thing you really have to do. Okay, so now let's look at the standard error. You know, here's a different formula, standard error of a point estimate, but I expect that I'm going to see a lot of similarities here. If I had to find this one, I know how to get my t sub alpha divided by 2 value. The S is going to be given, the N is going to be given, the X bar is going to be given, and if it's not, then you use your calculator to find it, okay? All right, so sometimes other than the population mean, the experimenter may also be interested in predicting values. What is the possible future value of an observation? Well, when that is being asked, then we construct a prediction interval. Okay, now when you receive all of the formulas, they will either directly be with the question that you're being asked or they will be labeled. So this is the formula. Obviously, it looks very different, and it is the formula that will give you a prediction interval. So if I want to predict a future observation value, this is the formula that I would use for that. Okay? All right, let's do it. Due to an increase in interest rates, oh my goodness, the First Citizens Bank received a lot of mortgage applications. Oh, a decrease in interest rates. See, I didn't even read that correctly. This is good news, right? A decrease in interest rates. The First Citizens Bank received a lot of mortgage applications. A recent, look at this, sample of 50. Mortgage loans resulted in an average loan amount of $257,300. It's a lot of money. The population standard deviation is 25,000. And I want to get a 95% prediction interval for how much the loan amount may be for the next customer. Okay, so with 95% confidence, at this point, you should know that's just 1.96. Every single time we did 95%, we had the Z sub alpha. Now, if it was T sub alpha, fine. I would need to make some adjustments because, of course, depending on the degree of freedom, that may be different. But at this stage, you should just know with Z sub alpha divided by 2, if you see 95%, you know that that's just 1.96. I don't think we need to exhaust that and go back to finding that on the chart and seeing which is closer. You know what that's going to be, okay? All right, let's get our prediction interval. I'm taking all of those values that I just identified and plugging them into this formula exactly where I see it. Exactly where, okay? So I have X bar plus and minus the Z sub alpha divided by 2 value multiplied by our sigma, and that is multiplied by 1 plus 1 over n. All right, let's plug it in. Our sample mean was 257,300 plus and minus 1.96, which is our Z sub alpha divided by 2 amount. That is multiplied by our population standard deviation, which is 25,000 as we identified. And that is multiplied by the square root of 1 plus 1 over n, and n is 50. So different formula for the prediction interval, but we know what to do. Let's plug everything in. $257,300 minus 1.96 times 25,000 times the square root of 1 plus 1 over 50. 207,812 and 43 cents. 207,812 and 43 cents. Notice how this time I actually rounded to the nearest hundredth instead of thousandth because we're dealing with money, right? So we needed dollars and cents, which is generally rounded to the nearest hundredth. All right, let's add now. Just changed it to a plus. So 306,787 and 57 cents is our upper bound. 306, 787 and 57 cents. There is our upper bound. What an amazing prediction interval. So this is saying, based on the parameters that we've had so far, the loan amount for the next customer that comes in, we have a 95% or 95% certain that the loan amount that they're approved for is in between 207,812 and 43 cents and 306,787 and 57 cents. Okay, there is our prediction interval. All right. Okay, so the prediction interval that we did just now was a prediction interval when we have a value that is known. Our variance and our standard deviation is known. Very subtle, but pay attention. You see how this says known? I don't know if you could see where I'm writing. Put it in red there. Known, right here. And I notice that I have sigma there. Well, this next formula, it clearly says our variance is unknown. And it's very subtle, but there's an S here now. That's the only difference. I mean, come on. Okay, so let's look at example 7. A meat inspector has randomly selected 30 packs of beef. Okay. I hope you see then our N is 30. 30 packs of 95% lean beef. Now, don't let that 95 confuse you. That 95% lean beef has absolutely no relevance to this problem at all. It's just telling us how lean the beef is, right? You need to read the problem so that you avoid making a silly error. The prediction interval, and I know I'm jumping ahead, is actually 99%. Okay, so don't mess that up. All right, our sample mean, look at the different language. The sample mean is 96.2. And notice our percent is already allotted in the problem. They already said, look, it's to assume a percentage anyway, so we don't have to convert that to a decimal or anything. We can just use 96.2. Standard deviation is 0.8%. Of course, we could still just use 0.8. Okay, the formula already allots for the percentage, and now we have a 99% confidence interval. Well, look how we've done this the same way every single time, right? I find my alpha, which is 1 minus 0.99, which gives us 0.01, and then we need t sub alpha divided by 2, which is t sub 0.0 and then 105. Okay, that's fine. But we know we need a degree of freedom. Every time we're using the t table, we need a degree of freedom, which is denoted with that phi n minus 1. So our sample size is 30. So 30 minus 1 gives us 29. So I need to go to the chart. I need to find t sub 0.05 with 29 degrees of freedom. Okay, let's find it. Okay, so this time we're at t sub 0.005. Let me double check. Yes, 0.005, degree freedom 29. Do you see it right there? 2.756. T sub 0.005 with 29 degrees of freedom, right there, 2.756. All right, let's put it all together. I'm actually going to go up to the formula just so that it would be easier for you to see where and how I'm plugging this in. I know we've done this many times. I'm following this formula now. We don't have sigma, we have S instead, but just making sure that you're with me so that we can all be on the same page. I'm going to do it right here where the formula is, okay? Our X bar, 96.2. Our T sub alpha value, 2.756. Our sample standard deviation, 0.8. That is multiplied by 1 plus 1 over the sample size. Our sample size is 30. Okay, so plugging all of this in, 96.2 minus, I'll do the lower bound first, 2.756 times our sample standard deviation times the square root of 1 plus 1 over 30. Lower bound, 93.959. 93.959. Okay. And we are expecting our upper bound to be 98.441. And this is our next confidence interval. Okay? Keep in mind, this is for the problem, below, but I'm just doing it so that you can see the formula that I'm using and understand where that's coming from. Okay? So now let's talk about outliers. This is something that you discussed, in depth in Statistics 1 and really in Statistics 2. A lot of statisticians are very interested in the outliers of a data set. Why is this one number or these numbers so much different than all of the other numbers? Right? If I have a value that falls well outside the pattern of the data, then that's considered to be an outlier. So I have what is predicted, right? I don't know what my population mean will be. However, using the sample mean, I can get like 95% certainty, 99% certainty that it would fall in this value. If it doesn't, then it's an outlier, okay? So let's talk about tolerance limits. Okay, for a normal distribution of measurements with unknown mean and unknown standard deviation, we can compute our tolerance limits by this formula. Okay, X bar plus and minus KS. So what is K? K is the value that is determined so that you can assert with a certain level of confidence that the given limits lie or contain at least a portion of those measurements. All right, so the formula is pretty straightforward. X bar plus and minus KS. We just need to be able to find K. And for many of you, this is probably the first time you've seen that variable. So using the information that we found in example 7, okay? In example 7, let's see what was our data there. Okay, so the X bar was, or the N was 30, the X bar was 96.2, and the S was 0.8. Okay, here was the value. This is the information in example 7. So let's go ahead and rewrite that here. In example 7, we had, this data. X bar, what was it? 90, oh goodness. 96.2, 30.8, okay. So our X bar was 96.2%. We had 30 in the sample, and we had an S value of 0.8%. Okay, so we're using those same numbers. Okay, find a confidence interval. Okay, so we have two-sided. We have 95% bound, and we have 90% of the distribution of the packages of that 95% lean beef. Just keep in mind this. I hope that 95% lean beef is not throwing you off. Here's the point. Pay attention. We're introducing a new chart that involves our gamma value, and that's how we're going to find the K. Okay, we have our X bar, which is a sample mean. We have our S, which is a sample standard deviation. In order to go to this new table, look at the new table here. It says tolerance factors for normal distributions. In order to go to this table, we need three things, okay? We need the confidence level. We need the portion, or the proportion rather, of the population that we want to cover. And we need the sample size, clearly. Okay, so now, what is our confidence level for this problem? It is 95%. Okay, so that confidence of 95% gives us an alpha of 0.05. Okay? Then we also want the proportion of the population that we want to cover. So we want 90% of that. So that is 0.9. And then our sample size, N, that's 30. All right, now let's go to our chart. We don't have a one-sided interval. We have a two-sided interval. How do I know? Because it says it right here. Okay. Our alpha value, so we're on this side. Our alpha value, that gamma value, is 0.05. How do I know? Because that's the difference between our confidence interval limit, or level rather, and 1. And then what is the amount we want to cover? 90%. So I'm in this column. And what is our N value? 30. Goodness gracious. So K is 2.14. Okay? 2.14. All right, it took us, some time to find that, but probably because this is the first time you've seen that new chart, let's just find our tolerance limits. Our mean for this problem, we're using the same mean as we did before, 96.2. Our K value we just found to be 2.14, and our sample standard deviation from the previous example is 0.8. Very basic formula, but we did obviously have to find the K. And in order to do that, we needed the three things that I mentioned. All right, let's very quickly plug this into our formula. 96.2, I'll do minus first, minus 2.14 times 0.8. Lower bound, 94.488. Okay, and our upper bound, just put a plus there, 97.912. And that's it for this one. So that's how to get our tolerance intervals based on the values that we have there. Okay? All right. Let's go on. Now we're getting into two samples, estimating the difference between two means. So if you're wondering, when would we use this formula as opposed to the formulas we've used before, it's pretty basic. If you see two sets of data, then you need to use the confidence interval for the difference between two means. But notice we've got two of those as well. Here, our values are known. And for the second one, both are unknown. Okay, and we have a pooled estimate of variance. Okay, so there's some details, extra details that we have when they're unknown. All right, let's have a look at it. Well, yes, it's a lot to read, but it should be quite clear if we just find everything. We've got a study conducted, 2 types of engines, A and B. So we've got 50 experiments in type A. Okay, so I'm just going to put my type A value here. N is 50. Okay. 75 experiments done with type B. So we have our type B. N is 75. The gasoline used and other conditions were held constant. The average was 36 miles per hour for engine A. And it was 42 miles per gallon for engine B. We want a 96% confidence interval. So alpha is 0.04. And let's see. Oh, they want the interval on B minus A. Okay, fine. That's fine. So since it says B minus A, we have to subtract differently. Okay, we actually have to subtract using the B value first, and that's fine. We can very easily do that. Let's go ahead and do that now. So that actually would be 42 minus 36, which is clearly just 6. Okay, fine. And then population standard deviations are 6 for engine A and 8 for engine B. All right, we have all of our data. Let's actually plug into that formula. Now, I'm going to be going back and forth because here is the formula. I need it, okay? So we subtracted our mean values already and got 6. We need a z sub alpha divided by 2 value. We have not done this one before, so we have to go find it. Our alpha value is 0.04, so we need z sub 0.02. That in half. It said z sub alpha divided by 2. Where am I getting that from? It says it right here. Z sub alpha divided by 2. Z sub alpha divided by 2. Okay, so I need to find that. So the chart only gives me areas to the left. So let me first subtract 0.02 from 1. When I do that, it's clearly 0.098. Now let's go to our chart. Okay, 0.98. I hope you're looking. All right, so according to this, pay attention now. I'm looking at the closest value to 0.98, and I see 0.9798. That's 2 away, and 9803 is 3 away. So clearly, this one is the closest, 0.9798. And the z-score associated with that is 2.05. 2.05. Okay. So let's go ahead and plug that in. Well, the rest of it, just plug in the values that I have. I've got sigma sub 1. It honestly doesn't matter as long as I keep them together. They've labeled it sub 1, sub 2. It doesn't matter. As long as I make sure I keep the set together. You know addition is commutative, so it doesn't matter. I'll just do A first. That's 6 squared over that first n, 50, plus 8 squared over that second n, 75. All right, let's plug this in. 6 plus and minus. I mean, I'll do it together. I've been doing it together all this time. Okay. I'll do the minus first. 6 minus 2.05 multiplied by the square root of 6 squared over 50 plus, no, I need to stay under there, plus 8 squared, goodness, 8 squared over 75. So my lower bound is 3.429. Okay. And my upper bound, by just putting a plus sign there, 8.571. And we're done. Okay. Done with example 9. I believe we only have 2 more. Let's keep trolling. Okay, so this one, very similar. The only difference is both the variance and standard deviations are unknown. And so instead of Z sub alpha, I'm going to use T sub alpha. But I do have a pooled estimate of variance, so I need to find that as well. How do I know? Because I see that SP here in the formula. So I probably need to find that first, okay? So here we have lots of different things here. But no matter how lengthy the problem is, we're looking for some very specific things, okay? So what are we looking for? Well, it says here 2 independent sampling stations were chosen for a study, one located downstream, the other located upstream, for 12 monthly samples collected at the downstream station, okay? I'm just going to put downstream, okay, N is 12. We had a mean value of 3.11 and standard deviation of 0.771. And then I guess we had upstream. Clearly it's 10. So N is 10. Our X bar sub 2 is 2.04. And our S sub 2 is 0.448. What do they want? A 90% confidence interval. Okay, so now pay attention. If our confidence interval is 90, then alpha is 1 minus 90, which gives us 0.1, and we have T sub 0.01 divided in half, which is T sub 0.05. Well, what are our degrees of freedom? Remember, we have to have a degree of freedom to go to the T-chart. And the formula for that, N1 plus N2 minus 2. Does it have it here for us? Oh, good. That's our degree of freedom. So let's find the degree of freedom quickly. 12 plus 10 minus 2, so that's 20. Let's go to the chart quickly and find that. T sub 0.05, degree freedom 20. So here's degree freedom 20, T sub 0.05. I hope you could see there 1.725. I can't write on this one, but hopefully you can see 1.725. Okay, so we have that. And we have everything else. So let's just go right to the chart. The first thing I need to find, so it's a lot of stuff here to plug in. The first thing I need to find is our pooled statistics. I'm going to plug in everything exactly as I see it, and I need you to follow along. N minus 1, that's 12 minus 1, times our S sub 1 standard deviation, 0.771 rather, squared, plus N2 minus 1. Our N2 was 10 minus 1. Our second standard deviation was 0.448, and we're squaring that. And all of that over 12 plus 10 minus 2. All right, let's plug in that. And since we're using that number for a different value, we need to make sure we write enough variables so that we don't mess it up, okay? In the numerator, we have, 12 minus 1 is just 11. Let's not waste time there. 0.771, and we're squaring that, plus, and then we have 10 minus 1, which is just 9. No need to put that something extra there. 0.448, and we're squaring that, and that is all over 12 plus 10 minus 2. Answer 0.4172, let's just go 4 numbers, 0.4173. That's our pooled statistic. Okay, taking that, plugging it in here where we see it, let's plug in everything else and get our value. Okay, looks like I need to subtract my x sub 1s. Let's get that. Okay, so x bar sub 1 minus x bar sub 2 was the first thing that they gave us. So 3.11 minus 2.04, what is that? 1.07? Okay. Now, I keep jumping back and forth because I need the formulas. I don't know what they are. So, yeah, that's why. But you have everything in front of you. So I'm plugging into this formula exactly. Okay, I just found this, 1.07. The T sub alpha value we found a second ago. $1.725. Our pooled statistic, 0.4173. And that is multiplied by the square root of 1 over our N1, 12, plus 1 over our N2, 10. Let's plug everything in. 1.07 minus 1.725 times, what was our, oh dear, our SP value, okay. For some reason, I'm wondering, is that, we have 0.417 there. I'm wondering if this is a typo. Should that be SP squared. Okay, our SP squared value is 0.4173. This just says SP without the square. So I have a feeling I need to take the square root of that. Notice it. See that? That SP doesn't have a squared there. So let's very quickly do that. The square root of 0.4173. So 0.645 or 0.646. That's what should be there. 0.646. Okay? Times the square root of 1 over n1 plus 1 over n0. Okay, answer 0.593. And let's get our upper endpoint by just adding a plus to this. 1.547. There is the answer for that. I am nearly out of time. I actually have a class at 6. Here's the answer to, let's see how much we have to do for example 7. Okay, I do not have time to do example 7. I only have 5 minutes left. And I'm noticing that this one is virtually identical to the one that we just finished. I mean, the only difference is instead of both of them being known, right? This one, it is unknown. So instead of z sub alpha divided by 2, like this one, oh, actually, it does have t sub alpha divided by 2 as well. But it looks like this is the difference between two means both unknown, and this is also the difference between two means both unknown, but the standard deviations and the variances are different. Okay, so yes, it's both a t distribution. However, the second one, both are unknown, but they are different. And for the one we just finished, both are unknown, but they are understood to be the same, equal. Okay, so take a second and see if you can figure this one out on your own. I will likely do a part 2, even though I really don't want to do a part 2 with just one. So I may just write up the solutions for this and post it on Moodle. In the meantime, here is your quiz. Notice that this quiz comes directly from one of the earlier examples. It looks like just example 1. I do want a 95% confidence interval as well as a 99% confidence interval. I've also included the formula to make it a lot easier for you. And this, of course, needs to be uploaded to turn it in Moodle by the appropriate due date. Take care, everybody. Bye-bye now.